continuing of the last class, already we have discussed the Horn-Banach theorem and its applications and some other also. Okay. Now already we have discussed the seventh topic. Now that is the seventh topic is open mapping theorem, and before that we have discussed the Berry category theorem also. Okay. Already Berry category theorem we have introduced in the first year real analysis. Now what is the second category? Okay. What is the second category? And according to that second category definition, we have discussed the Berry category theorem. Now let us have to see. Please screen share here. Please see the seventh unit. Okay. Students, just you have to see the open mapping theorem. This is the seventh unit. Very most important in the final examination. Don't deviate especially this session and tomorrow's class also. Okay. What is the first category and second category and nowhere dense? Now these definitions already we know that in the first year using second paper real analysis. And according to those definitions, we have discussed the Berry category theorem. Okay. And before that, what is the first category? What is the second category of sets? And first of all, a subset of capital A of a metric space is said to be a nowhere dense if its closure has empty interior. When it is the closure has empty interior, and that is called closure has empty interior is called nowhere dense. And according to the definition, once again, just we have discussed the those definitions, nowhere dense, first category and second category definitions. Okay. Now what is the nowhere dense? Now here we are taking the any one of the metric space here, and that metric space. Okay. Please see this one. Okay, students. Now, first of all, we are taking the any one of the metric space here. Now, that metric, according to the metric space of the subset is said to be a nowhere dense. What is the meaning of nowhere dense? Okay, nowhere dense means then the metric space of the subset when it is the closure and it has empty interior. Okay, closure and has empty interior. Closure is denoted. Suppose capital AB, any one of the subset is there. That closure is capital A. Capital A. A closure means A bar. Okay. A bar equals to empty interior means that is the empty part. Okay. Closure A equals to empty. So that is called nowhere dense. Okay. Now, a subset of a metric space is the first category. What is the meaning of first category? The union of countable family of nowhere dense sets. Now, according to the nowhere dense sets, the union of countable family of nowhere dense sets is called first category. If it is not first category, that is called second category. Okay. If it is not first category, so that is called second category of this part. And according to that, here capital A is nowhere dense. Now, a necessary and sufficient condition, it is each non-empty open set contain an open sphere disjoint from subset. Okay, already we learned in the first year part. So the theorem. So this is this remark represented as one of the theorem is here in the first year real analysis. Okay, first of all, so what is the nowhere dense? What is the first category and second category? And according to these three definitions, we have discussed the Berry category theorem. Simply, what is the statement of Berry category theorem? Every complete metric space is of second category. Okay, is of second category means if it is not first category, that complete metric space of the every part complete metric space is of second category. So that is the simple definition of simple statement of Berry category theorem. Now, according to that complete metric space, first of all, so you have to take in the one of the complete metric space. Now, what is the first category of the part? Union of the sequence of its subsets. Then the closure of at least one set in the sequence must have non-empty interior. Okay. No, but the first category means, if it is not a first category means the union of family of countable the union of countable family of no variance is the first category. If it is not, so that is the second category of part. Okay, that is we must prove that that is non-empty interior. So that is called the second category definition. So here that is the second category means the union of sequence of its subsets, then the closure of at least one set in the sequence. At least one set in the sequence must have non-empty interior. Okay, so that is the second category definition. So simply stated as every complete metric space is of, so this is the definition of second category. So that is the simple statement. Now, according to that, just once again, must have first of all, once again, I will explain here then the proof of Berry category theorem. First of all, so you have to take in the one of the sequence AN is there. The countable union of the part, say that is capital X. In a metric space, the countable of the sequences. So, uncountable of the part. Okay, that is n equals to 1 to infinitive. The union of uncountable part of the sequence is, say, capital X. Suppose that the closure of the sequence of interior is empty. Now, according to this one, that is the non-empty of this part. First of all, so you are taking the empty part is there. Closure of the sequential of the interior is empty. So, put n equals to 1, 2 and so on. So, that is the closure of A1, closure of A2. So, closure of interior of A3 and so on. So, this is the, it denotes the interior of the set. A bar denotes this is the A bar or A power C, whatever it is. So here A bar means that is the closure of A. That is the bracket of A or interior of A. Closure of A means interior of A. So that is the interior of the set. Here AN is nowhere than subset of capital X. So here capital X is the metric space. Here we are taking the AN is the one of the nowhere than subset. Here then the metric space is open, and first of all, so you have to take in the one of the subset is A1. Suppose A1 is nowhere dense, by the above remark, we can find an open sphere S1 of radius less than 1 and which is disjoint from A1 is there. Okay. Now, here let us consider concentric closed sphere F1. Now, the entire closure of the subsets is denoted by capital F and open subset is denoted by capital G according to this material. Okay. According to the entire all the analyzation, now we are taking the F is closed. Here, concentric closed sphere is denoted by F1 and whose radius is 1 by 2 of S1. Okay, S1 is the first sphere of the nowhere dense subset. Now, interior of F1 is open and A2 is also, okay, nowhere dense. Okay, A2 is also nowhere dense. Hello. Okay now. Hello? Are you follow? Now that the interior of F2 is, suppose interior of F2 is open and A3 is also nowhere dense. Okay. And according similarly, here the number of here according to the third concentric closed sphere of the open sphere is S3 and whose radius is less than 1 by 4. 1 by 4 means 1 by 2 square and disjoint from, this is the third subset of the part. Continuing in this process, now we have to discuss the closed sequence is Fn is there and the closed sets of X and diameter of Fn. This is it represented as diameter of Fn is converges to 0. Okay. Now d of Fn represented as diameter of the set Fn. And diameter of Fn means that is the supremum of diameters in between A1 and A2. So A1 and A2 now these are belongs to the concentric closed sphere of Fn. Since capital X is complete by Cantor intersection theorem. Now, what is the Cantor intersection theorem? An arbitrary intersection of the concentric closed sphere is non-empty. That is the simple statement. Okay. Now, suppose on the concentric closed sphere of the part, say that one of the element is small x and small x is contained or equal to capital X. Student, listen carefully here. And according to this construction of the set Fn, X is not in any of the sets An. Suppose n equals to 1, 2, and so on. So here finally, that element small x is also belongs to capital X, and X is not containing arbitrary intersection of the concentric closed part. So that is this value is an equivalent to capital X. So X is not consisting of capital X. So that is the contradiction. Suppose here already we are taking the x belongs to x, but it is not, x is not in x. Yes, now that is the given the statement. So finally, complete metric space means every Cauchy sequence or converges to a point. So the point is small x. This is of the second category of this part. So non-empty means now that is the represented as that element represented as capital X. So that is the proof of this theorem. Okay. Now, finally, we will discuss the open mapping theorem. Now, this is one of the most important theorem in the functional analysis. What is the open mapping theorem? Now, this theorem was obtained by Banach. He is one of the great mathematician in the entire part of analysis, especially functional analysis and operator theory. Now, that mathematician represented so many theorems: Banach-Stone theorem, Hahn-Banach theorem. And now, Banach is also connected with the Hahn. So, the theorem is represented Hahn-Banach theorem. Already we have discussed in the previous class. Okay. Now, the theorem was, the open mapping theorem was obtained by Banach. Now, he was born in 1929. Okay. Now, Banach, now, first of all, we must know that each and every mathematician, first of all, we know that yes, either algebra or analyzation, whatever it is. So those mathematicians, we have those mathematicians are represented, or so many theorems are here. Okay. Now here Banach is also one of the great mathematician. Now that mathematician was discussed in the open mapping theorem. So the theorem, according to the theorem, the above Berry category theorem, according to the Berry category theorem, we are taking the one of the sphere. So that is S of S R of X or S of XR. Students, listen carefully. Now, it read as the open sphere or sphere of the center is small x and the radius is small r. The sphere represented as S base R of X or S of X and R. Now, that is the sphere. That sphere represented in the terms here small r be its radius and x be its center. We are taking the one of the sphere is there. A set of points which are at a constant distance from the fixed point is called a sphere. That is the definition of a sphere. That sphere of the center, middle of the part is small x or open ball, whatever it is, or open ball or open sphere, that is a small bracket. Suppose you are represented as the square bracket of the part, that is the closed sphere of the part. Here we are taking that sphere is open sphere and x be its center and r be its constant distance is small r, that is the radius. Okay. Now, this sphere centered with at origin and small r its small r as radius. Suppose put x equal to 0. So that sphere of the center is center at origin and we are taking the radius is small r. Now we have, according to that through the origin of the radius of the sphere. Now the just we must see this lemma, that that theorem. What is that theorem? Open mapping theorem completely depends upon the lemma is there. So lemma is that is the basement of the open mapping theorem. According to this statement, we will discuss the open mapping theorem. First of all, just you have to see here. Please stay on the line. Please stay on the line. Please stay on the line, students. Please try to understand here. Now these two classes or these two sessions very most important in the final examination. If you have any doubt, please contact as and personally through WhatsApp. Already I have given my personal number. Personal number is there. That is my WhatsApp number. Number of times I told here. Okay. Please stay on the line. Please wait for 2 minutes. Okay, students. Now this lemma, here we are taking the B and B dash. There are two Banach spaces. What is the Banach space? Already from the beginning of second session, now we have introduced the definition of Banach space. What is the Banach space? A normal linear space which is complete. That is called a Banach space. Okay. Now we are taking in any two Banach spaces and the connected map is continuous linear transformation is denoted by capital T. Now that transformation, that transformation represented as the continuous linear transformation. Okay. Already there are so many theorems we have discussed in the previous classes depends upon the continuous linear transformation. Now we are taking if capital T is continuous linear transformation, it varies from capital B onto B dash. Okay, students. Now this is the continuous linear transformation. Okay. Then the image of each open sphere S or in B. Now B is the domain of this part. Depends upon the mapping. Okay, B onto B dash is there. Now in the capital B is in the domain of the open sphere is SR and codomain of the range of the part is B dash of the open sphere is SK dash. Now that is here radius is smaller and here the image of the radius is K. Okay. Now here suppose capital T from B onto B dash is a continuous linear transformation. Then the image of each open sphere S or in B, it contains an open sphere SK dash in B dash. Suppose put R equal to K. Suppose SK in B is there and in the same part image of the open sphere is also in B dash is there. That is the simple statement. And according to that statement, we will discuss we must prove the proof of this theorem. First of all, so we are taking the one of the radius is small r. That small r is non-negative part, so that is greater than 0. And in the same manner, and corresponding this radius and put r in the replace of there exists KB is also one of the radius, that is also non-negative part, K is greater than 0. So this K, this existence of the radius in image of this part, in the image on open sphere, that is SK dash that contains T of SR, because SR beats open sphere of the radius in capital B, and then the transformation of the part is in SK dash. SK dash means that is the B dash of this part. So SK dash is also belongs to B dash is there. So first of all, so we observe this one that open sphere of the transformation represented as capital T of SR can also be represented as put a first radius R into S1. So R is the constant of this part. That radius is constant because that is the constant distance. Radius means small r into T of S1. Now what is the meaning of SR? So radius of the open sphere represented as in the roster form. Here x being one of the element, that is the center. Center it's given in the that open sphere. So then the center according to the norm condition is less than small r. So norm x less than r. So this is also, it can be divided in throughout according to this condition. Norm x by r less than r by r means 1 is there. Now correspondingly this can also be written as rx. Now my cross multiplication, put a enter the that set is multiplying with small r. Small r beats radius. Rx from norm x less than r into 1 is small r. Now r of here r is common. R of x from norm x less than 1 is there. Small r, it's small r be the common part of given the set and before that set. So here this value is because replacing of r by 1 is there. So this is s1 is there. So that value is r into s1. Okay, suppose the transformation is onto, it follows that B dash, image of the Banach space that represented as the countable of the union T of Sn. So B dash is also a Banach space. So by Berry category theorem, already we have discussed the Berry category theorem. There exists at least one set S or not. S n naught, such that the closure of T of Sn naught contains at least one interior point, that is y naught. So T of Sn naught represented as y naught is there. Y naught is also belongs to the closure of T of Sn naught. So that is also one interior point. So we are taking the T of S n naught of the element is y naught. This is at least one interior point. So that interior point here, let y be an interior point of closure of T of Sn naught, which implies that there exists open set capital G such that here the what is the enter the all the open sets represented as capital G, closed set represented as capital F. Enter the analyzation of this part according to this material. Okay. Now so many mathematicians are also represented as the some other also represented as the open sets. Capital T is there, or capital G is the capital capital Y, or capital T is also represented as the closed sphere, and those some other references also references. You must thoroughly practice the references books in analyzation. So similarly here, especially this is functional analysis or analysis according to our material. Here capital G be the open set and capital F be the closed set. That is our representation in this material. Here that open set of the element is Y. So Y is also consisting of given the open set. So that is also contained or equal to that open set is also contains contained or equal to closure of Tsn naught. So this is the one of the interior point. So when the interior point students, when the open set means a neighborhood, each of its points that is called open set. So at the same time, it having some interior point is there. So here particularly YB it's a limit point of T of Sn naught. Okay. The neighborhood G of already just recently discussed here. Open set of the neighborhood of Y must contain the point Y naught of T of Sn naught. So finally, Y naught is also, that is the initial interior point. Initial interior point it is containing capital G. So that is also contained or equal to, closure of Tsn naught, which means that Y naught is an interior point of closure of Tsn naught. So simply just in the final examination, just you have to represent this one. Only represented this is that's enough. Okay, because this is the big theorem is there. Some that is drafting is not in sometimes that is not necessary here according to the given the steps here. Okay. Here Y naught is also interior of T of Sn naught. So Y naught is consisting of T of Sn naught. Now consider the mapping. F varies from B dash onto itself, because onto map means image is also represented as the image of this part. Now FB any one of the mapping, it is defined from B dash onto itself. So finally we F of Y equal to, in between the differences is Y, in between Y and Y naught. So that difference is denoted by Y minus Y naught, which is a homomorphism. So when the given the mapping, homeomorphism means, so when the function of the part on the image of the function of the part, when it is onto itself, so that is called homeomorphism. So clearly, what is the meaning of homeomorphism? The given mapping is 1, 1 and onto. So before that mapping, so that is defined F from B dash onto itself. Here Y and B any one of the sequence. According to that, Y and B the one of the interior for Y naught, Y1, Y2 and so on. Well, that is also represented as one of the sequences Y and B, one of the sequence. Here n being a natural number is there. Here, okay. Now, here the yn be any one of the sequence in B dash such that yn converges to the point is y, because y is a limit point. So this is that limit point is called convergence point. So f of yn equal to yn minus y naught, and it is also converges to, because yn converges to y. So according to this, this can also be written as f of y, already before this one. throughout this mapping, assumption of the mapping f of y equal to y minus y naught, f of y1 equal to y1 minus y naught. Okay, and similarly, if yn be any one of the sequence, that function of the sequence represented is yn minus y naught. Because already we know that yn converges point is y, and replacing this one, so yn minus y naught converges to that converges point is y. We are taking the converges point y minus y naught. So this value is an equivalent to f of y. So f of yn equal to f of y. See, that is already we have derived here. So finally, given the function is continuous, because this represents that definition, absolute of f of yn minus f of y is less than epsilon. So that is the condition of given the function is continuous. Okay, and we are taking the in addition. Okay, in the preliminary interior point is the primary interior point is y naught, and n of the interior point is yn. So both are adding here sum of the value of the function. So that can also be written as we are taking in between yn plus y naught minus y naught. Okay, f of yn equal to f of yn plus y naught. So replacing yn by yn plus y naught in this in the above condition. So according to this condition, we must write f of yn plus y naught. So replacing yn by yn plus y naught minus y naught is there. Okay. So that value is an equivalent to yn. Okay. What is the image of the part of yn? So inverse of the value, image of an inverse equal to inverse of the image. Already we know that property. So f inverse of yn equal to, what is the inverse of this part? So yn plus y naught converges to, okay, what is the replacing of yn by yn converges point is y. So that is y plus y naught. So this is the inverse of the function. So that value is an equivalent to f inverse of y. So this function is the inverse of the function is also continuous. So assumption function is continuous and inverse of the function is continuous. Inverse of the function represented in terms of yn plus y naught replacing by yn. So according to this one, f inverse is continuous. So from the above step is f inverse of yn equal to f inverse of y. Now here, given the function is a homeomorphism of b dash onto itself, we show that 0 is also an interior point of T of S1. Okay, that is the first square of the transformation. Interior point is 0. By using the above the function, 0 is an interior point of closure of T of Sn naught converge equal minus y naught. By the first equation, what is the first one? That is the assumption. According to the assumption, see this one. By first condition, y naught is an interior point of closure of T of Sn naught. Implies that here the open sphere, when it is existence of the centered at y naught is contained, because this is the center, okay, which is contained in closure of T Sn naught. So contained at y naught, open sphere of the contained at y naught, that is also contained in closure of T of Sn naught, because this is the open sphere of the transformation. Then its closure of the interior point is y naught. So that the function of the closure of T of Sn naught is an open sphere, because given the function is open map. Now this is the open map because all the neighborhood of each of its interior points. So that in those interior points depends upon the functional part. It has open sphere centered at f of this value is say y naught is there, which is contained in it. Okay. So that the definition in between it, closure of T of Sn naught minus y naught, it has that value is f is there. So f of y naught equal to replacing of this one y naught minus y naught. So that value is 0. So that is a 0 is an interior point. Already we know that 0 is a interior point. This is the second equation. So y naught is in a T of Sn naught. We have T of Sn naught minus y naught contained are equal to T of S2n naught. So continuing in the same process. Okay, T of Sn naught minus y naught, here one of the element is y. So there exists of the element here x be any one of the element in Sn naught such that y equal to, that is this value represented as x is there, T of x minus y naught. because here x be any one of the element in the open sphere of the part. Yes, n naught. Here n naught be the that is center. Okay, so that center n naught replacing by x is there. So t of x minus y naught, that value is say y is there. Where here what is the norm? Center of the norm is less than n naught. So x represented as x value, then their norm is also less than n naught is there. Or so in the same process, norm x minus x naught equal to norm x plus norm x naught less than, this value is also less than n naught, and x naught value of the norm is also n naught. So that value is 2 n naught is there. Okay. So finally here x minus x naught belongs to s to n naught. So students, are you follow here? Students.
Yes, sir.
Okay, once again, I repeated here, these two classes are very most important in the final examination, and previous classes are also just you have to refer, and that is also one of the most important, successfully achieved easily to get 60, 65 marks. There is no doubt. Okay. Now, especially in this session, please wait, please stay on the line.
Yes, sir.
Okay. Especially in this session, we will discuss the Berry category theorem. What is the no-variance? Just have to repeat it here. Okay. What is the no-variance? First category, second category definition, and Berry category theorem. Already we have discussed in the first half an hour. Okay. Now, according to that one, before that open mapping theorem, we will discuss given this lemma according to through the Berry category theorem. Okay. There are so many representations of the open spheres S to n naught in between x and x naught. So then the transformation value is say is also belongs to T of, because this value is S to belongs to S to n naught is there. So transformation of S to n naught minus y naught is also contained or equal to this value is S to n naught. In the same manner, this is also a homeomorphism. Okay, which is given the function is 1, 1 and on 2. So there are number of radius represented as the x belongs to n naught and x be its center. Then the closure of interior is also represented as here given the function is a homeomorphism. Then their function is also f of closure of t of s n naught. Okay. So when the third in the in between third and fourth equation already we hello? From third and fourth equation, we get closure of T S n naught minus y naught is contained or equal to closure of T S n naught. So closure of T n, because second equation through the origin, it is an interior point. Because putting here the center at origin, so 0 origin is also an interior point. So that is that origin point also belongs to the closure of T of S n naught minus y naught. And it is also in the same manner closure of T of S to n naught. Okay, this can also be written as 2n naught into T of S1 is there. Because SR equal to, what is the meaning of SR? R into S1 is there. Okay, what is the, okay, this is the R into S1. In the same manner, because 2n naught into T of S1. So, origin is an interior point of this value is 2n naught represented as that is also closure of TS1. So, yeah, finally, S epsilon dash, because here epsilon be any radius, given the existence of the open sphere, that epsilon is also always greater than 0, because center at origin in B dash. So, which is contained in a closure of TS1. So, finally, S epsilon dash contained are equal to closure of TS1. Okay, we show that S epsilon dash contained are equal to T of S1 is there. There are so many center at origin, so many radiuses are there. Now S epsilon dash contained are equal to T of S3. Now that can also be written as T of S dash of epsilon by 3 contained are equal to S dash of epsilon by 3. It can be divided into the 3 parts. So S epsilon by 3 dash, because image of the open sphere contained are equal to T of S1. Now it is consisting of 3 parts of the radius. Okay. Now, y be any one of the vector. This is in B dash. So, norm y is also less than epsilon. So, y is also belongs to S epsilon dash. Y belongs to closure of T of S1. Finally, y is a limit point of T of S1. So in between y1 and y3, so condition y3 is taken here. There exists a vector. There exists a vector y1 in T of S1. So norm y minus y1 is less than epsilon by 2. Okay. So y1 is containing of T of S1. So y1 equal to, now replacing of here x1 be its center of first open sphere. So y1 equal to T of x1. For some here x1 belongs to S1 is there. So what is the condition of the centered of the norm? Norm x1 is less than 1. Already previously we have to discuss here. And commencing of the first part of the theorem. S epsilon dash contained are equal to closure of T of S1. So that can also be written as applying on multiplying with 1 by 2 on both sides in this condition. 1 by 2 S epsilon dash contained are equal to 1 by 2 into closure of T of S1. So this is S epsilon by 2 dash is there, because 1 by 2 into S epsilon dash means S epsilon into 1 by 2 dash. So that is S epsilon by 2 dash contained are equal to closure of T. What is the 1 by 2 into T of S1? This is 1 into 1 by 2. So that is the T of S1 by 2. So norm y minus y1 is less than epsilon by 2. Here y minus y1 is less than, it is also consisting of S epsilon by 2 dash. This is also contained or equal to closure of T of S1 by 2. So continuing in this process, here the y2 vector is there. So that is y2 vector is also belongs to T of S1 by 2. What about the condition? Such that norm y minus y1 replacing y by y minus y1, and in between y2 is there. We are taking the y2 vector from y minus y1, replacing y by y minus y1 through this condition, y minus y1 minus y2 here, because y2 is also another existence vector. It is less than epsilon by 2 square. So y2 equal to T of x2. For some here x2 is also belongs to S1 by 2, such that norm x2 less than 1 by 2. Now continuing this process, here xn be any one of the sequence in capital B such that norm xn less than 1 by 2 power n minus 1. And here norm of y minus of, replacing of y minus of y1 plus y2 plus so on, minus plus y minus of y1 plus y2 plus y3 plus so on yn. Okay. It is less than epsilon by 2 power n, and continuing this process the above step. Here what is the yn value through this one? Yn equal to T of xn. Now here limit, that is also represented as limit n tends to infinity to y1 plus y2 n terms. We are taking the replacing by yn is limit of y1 plus y2 plus so on plus yn. So that limit point of those sequential of the limit point is, say, y is there. So because that is the convergence point. What is the meaning of xn? The sum of the n terms. Sum of the n terms. That is the partial of the sum sequences is called a series. Okay. That series is denoted by Sn is there. Okay. Sum of the partial sequences means the entire this value can also be written as summation n equal to 1 to k sk is there. So that value is Sn is there. Here Sn is a Cauchy sequence in capital B. So that is the Sn value represented as the sum of the n terms of the sequence. So applying on both sides the norm value, norm Sn equal to norm of x1 plus x2 plus 1 plus xn. So enter this value cannot exceeds this it symbol read as cannot exceeds or less than or equal to into individual norms. So some of the norms, this is the parallelogram law. Some of the norms cannot exceed the norm x individual of their norms of the sum of the individual of their norms. So norm x1 plus norm x2 plus so on norm xn. So already we know that first norm of the center is less than or equal to 1. Second norm of the center 1 by 2, and third norm of the center 1 by 2 square, and so on. Finally this value is 1 by 2 power n minus 1, because this is the second norm of the sequence, that is 2 power please, hello, mute is there. Your phone is also mute is there. Okay. 1 plus 1 by 2 plus 1 by 2 square plus this center at the hello. So this of the norm xn represented as enter that value is less than 2 is there, because through the series of the notion, this value is an equivalent to eccentricity because this value less than 2 is there. Okay. So 1 plus, enter this value is an equivalent to 1. Finally, that value is 1 plus 1 is, that is the 2 is there. So norm Sn is less than 2. Okay. So Cauchy sequence means, and we are taking another positive integer m is there. In between the sequences Sn and Sm, there are two sequences of the difference of their norm is norm x plus xm plus 1. So write as Sn equal to x1 plus x2 plus so on plus xm plus 1 so on xn, and Sm is, and continuing of the process as x1 plus x2 plus so on plus xm plus 1 xm plus 2 so on up to xn. So all the sequences in between the now that is the cancelling of the part in between Sn and Sm, we are getting the values of remaining of the values is minus Sm plus 1, that is xm plus 1, minus of xm plus 2, minus of minus plus, so that is xm plus 2, so on up to xn is there. So Sn means in be x1 plus x2 plus so on plus xm plus 2 plus so on plus xn, minus Sm means minus of x1 plus x2 plus so on xm. So all the values are cancelled. Remaining of the in between of the values of in between m plus m and n is there. Up to m values are cancelled. Remaining the values is xm plus 1, xm plus 2, so on, xn is there. So each and every value, this value is less than or equal to, because 1 power 2 n minus 1. So m minus 1 plus 1 is 1 by 2 power m. That is the convergence point. And the next norm x plus m2 less than or equal to, that is also 1 by 2 power m plus 1. And this value is an equivalent to 1 by 2 power n minus 1. This is the geometrical expression. So according to the geometric progression, so what is the up to n terms of the geometric expression formula? E of 1 minus r power n by 1 minus r. Please note down s n terms in GP. So this value, how to determine this value? This value is entire the sum of the terms in GP is there. This is the first term, second term, up to n terms are there. So Sn formula is Sn equal to A of 1 minus r power n by 1 minus r. That is the number of terms in geometric progression, sum of the number of terms in geometric progression. So infinite in geometric progression is A by 1 minus r. That is the simple expression. Okay. Now this is up to n terms. We are getting the A value. First value is 1 by 2 power m, 1 minus. Okay. Now this is 1 by 2 power. What is that? R power n. R means that is the in geometric progression, second term by first term. So 1 by 2 power m plus 1 by 1 by 2 power m. We are getting the value is r. So 2 power m is cancelled. 1 by 2 is there. So 1 by 2 power, these are all n terms up to n minus m terms. By 1 minus r means this value, r value is 1 by 2. This is r power n plus 1. 1 minus 1 by r plus 1 terms. We are getting the values 2 power n minus m is there. By 1 minus r means r value is 1 by 2. How to get the r value? That is the common ratio, second term by first term. That is these terms in GP, geometric progression. So finally, we are getting the value is this is the entire that value converges to 0. Okay. Finally, here the sequential of the limit is say x. So given the Cauchy sequence converges to a point, that is called a complete. So that is called a Banach space. Now here capital B is complete, and before given the sequence is the Cauchy sequence in capital B is there. Now here the existence vector is a small x such that limit of Sn equal to x is there. So then the norm of x equal to norm limit Sn. So limit n tends to infinity to norm Sn value, enter that value is less than or equal to 2. So norm x is less than 3. So enter this value less than or equal to 2, and but the center of the norm is less than 3 is there. So here x belongs to S3. So that vector is also consisting the third sequential of the part S3 is there. So finally, we are taking the n terms. So this is y1 represented as tx1, y2 represented in the transformation part is tx2, yn represented in transformation is txn. So enter this value is t of x1 plus x2 plus so on xn. Transformation is common. So this value is an equivalent to Sn is there, T of Sn. So given the transformation is continuous. Students, listen carefully here. Now, very interesting of this theorem. In the final examination, this theorem is given. That is the long answer question. That is the 10 marks. T is continuous. We have limit Sn equal to x. That is the limit point. So applying on both sides transformation Tx equal to limit of T of Sn. Replacing Sn by y1 plus 1, yn is there. T of Sn value is y1 plus 1, yn. So enter that the limit point is say y. Finally, this value y is an equivalent to tx. So tx equals to y. Okay. So hence y equal to tx, norm x is less than 3. Here x is also, this is the meaning of x is consisting, S3 is there. So finally, y is also consisting a T of S3. And that the image is, we proved that y is also consisting epsilon b, it's a sphere. That sphere is in image of the open sphere. So that element is y. That is also one of the interior point. So y is belongs to, this value is an equivalent to T of S3 is there. Finally, S epsilon dash is also contained or equal to. So y is an interior point S epsilon dash. Y is also another interior point. Same interior point belongs to T of S3. So finally, S epsilon dash contained or equal to according to that condition. So this is same element belongs to S epsilon dash and T of S3. So we are getting the S epsilon dash contained or equal to T of S3. So multiplying with this is the 3. So we are getting the value is 1 is there. How to get the 1? Multiplying 1 by 3 on both sides. That is 1 by 3 into S epsilon dash contained or equal to 1 by 3 into T of S3 into 1 by 3. So we are getting the values T of S1. So finally, S epsilon, this value can also be written as S epsilon by 3 dash contained or equal to T of 3 by 3 means 1 is there. So S epsilon by 3 centered at origin given in the open sphere in the image of the Banach space, and it is also continued. This is also continued condition. Continued in T of S1. Okay. Now this is the very two peculiar theorem. Now this lemma is completely depend upon the open mapping theorem. Students, don't deviate here. Now this theorem much more important, very important theorem, and much more important lemma depends upon the open mapping theorem. Okay. Now here the open sphere is S epsilon by 3 dash centered at origin and B dash, and that is also continued in T of S1. So that is the lemma. Now just you have to direct theorem is open mapping theorem, and the above according to the above lemma. Okay, simple statement. Students, listen carefully. Now very interesting theorem in the functional analysis. One is the Horn-Banach theorem, Berry category theorem, open mapping theorem, closed graph theorem, and some other theorems are also we will discuss in the further session. Okay. Now that is the open mapping theorem. Now we are taking any two Banach spaces, say that is B and B dash, and the continuous map in between B and B dash is the continuous linear transformation B onto B dash. Then if given the transformation is open mapping. Very simple statement. Depends upon the above lemma. Okay. Students, listen carefully. Are you understand here? Please respond. Can you understand?
Yes, sir.
Okay.
Yes, sir.
Okay. Thank you. Already, students, listen carefully. One more student respond thoroughly. Some other also not responded here. Now, this is very struggled here online session. Please try to understand my situation. Each and every theorem we have to discuss in the from the beginning of the online class. Okay. Now that is a statement of B and B dash both are Banach spaces, and in between the continuous linear transformation in between the B and B dash, that continuous linear transformation is onto part. When the onto continuous linear transformation, so this is the transformation is open mapping. That is the statement, simple statement. Okay. So first of all, we are taking the transformation. Open is represented as capital G. So that continuous linear transformation of the open mapping. So open set T of G is open in B dash, because that is the transformation of the open part. So it is open in B dash is there. And before that, capital G is open in capital B. Okay. That transformation means mapping of the open is in B dash. Okay. So before that, then there is that is to prove that every point of K of G. So what is the meaning of open? So first of all, that image of the open when it is an interior point of T of G. So image means T of G. So before that, we are taking the any one of the interior. Okay, that interior element is say y. Now already we have discussed in the above lemma. Y belongs to T of G. So, and before that, according to the open sphere, in between the X and R, here X be its center in the open sphere, open set. Here X being the one of the element in the capital G is there. Here G must be represented as the open part. So, such that open sphere of the element is, say, small x. That element is also before that belongs to capital G is there. Okay. Now, here y equals to, so that open of the open means that is the transformation of the element, center of the transformation represented as Tx, that is also say y is there. Y is the image. So y be its interior. So here x belongs to G. G is open. There exists an open sphere S of X and R. So this is the meaning of open sphere. Simply that is S R of X. X be its center and R be its radius. And sometimes also referred as S of X and R. So this is the spherical part. Center of the element is X. Say that is center. And constant distance on the denoted by small r. So S of X or X and R contained are equal to capital G. So F of X, S of X and R can also be written as X plus SR. So that open sphere of the element represented as X plus SR, and applying the transformation. So that is KB any one of the existence element K greater than 0. So that is SK dash contained are equal to, already we know that SK dash contained are equal to T of SR, and before that K is the existence of the part greater than 0. So adding on both sides Y plus SK dash. So this element adding on both sides Y plus SK dash contained are equal to Y plus T of SR. So this element is also represented as contained are equal to T of G, because T of G means Y be it's one of the interior element. So that's why this element represented as T of G. So S dash of Y and K, S dash of Y and K. This value can also be written as S dash of Y and K contained are equal to T of G. Y plus SK dash can also be written as S dash of Y and K is there, because K be its radius and Y its center in the image of the open sphere. It is contained are equal to T of G. This shows that Y is an interior point of T of G. Okay. So here, that is also one of the interior point in image of the transformation. So that is one here that interior is arbitrary. It follows that T of G is open. That is the simple proof. Students, listen carefully. State and prove open mapping theorem means that is the simple proof. And some other students also, sir, this proof is very simple. Now, how to given the full marks? Okay, they have entire the theory completely depends upon the above lemma. That lemma is also, if you are interested, the above lemma is also replacing in this part, but not necessary here. Okay. Now that is the simple proof, and without the lemma, we can't explain the open mapping theorem. And in the examination, state and prove open mapping theorem means, so that is the simple statement and proof is that's enough. That the full the above lemma is not submitted in this theorem. Okay. And we know, first of all, so we must know that the above lemma is there. If you have interest,
lemma kuda ravala sir.
That is not necessary. Okay.
Okay, sir.
That is not necessary. If you are interested, you must replace the in between the theorem is there. Only lemma statement.
Okay, sir. Okay.
Okay. Okay. Okay. This is also one of the important theorems, student. So, in sometimes give any example which is not an open mapping theorem. So, in this time, just tell us one more thing is there. State and prove open mapping theorem. If it is not, give example, any shortable example. That is a simple short answer question. Any state, only state means a statement is also produced here. Not necessary of the proof. Okay, that very simple paper, functional analysis. Okay, direct theorems is also submitted here. Okay, now give any shortable example of which is not an open mapping. Means this example is also submitted there. Let here the capital B means that Banach space of the elements are system of real numbers. Image of the Banach space is Cartesian of real system. Now here B and B dash both are Banach spaces. Here given the domain of the elements are system of real numbers, and codomain means the range of the elements are image of the part is coordinates of the system of real numbers, that is x and y. Here x belongs to R, that is the domain element. But here coordinate elements, Cartesian product of the elements are Cartesian elements are ordered pairs, that is x and y. That is in the x and y is the ordered paired element in B dash is there. So that transformation B onto B dash, R cross to R cross R approaches to R cross R. So one of the element is x. So Cartesian product is x and x. So and another radius is x and x means here x is center and radius is 0. So that is the Cartesian product of the element is x and 0. When the radius is 0, so then automatically given the transformation is linear, continuous, but not onto is there, because radius is also approaches to 0. So that's why given that the transformation is not onto, so given the transformation of the mapping, transformation means mapping. So that transformation is not an open mapping. Simple representation, give any shortable example of which is not an open mapping. Only this example is also produced, replaced there. Okay, that is the simple solution. Okay, state open mapping theorem. Give any example of which is not an open mapping. Means first of all, you must present the statement of open mapping theorem, and second one is the example of suitable example of which is not an open mapping, means that is the example 7.4.3. So sometimes that question is also given in a short answer. Okay. Suppose according to my sense, now I will give this type of question, because so the number of students also they are thinking very broad-minded. Okay, proof is a very big proof is also produced represented there in the answer sheet. Give the good marks. Okay, that is not necessary here. Now, according to the question, you must replace the answer is there. You must replace the solution is there. Okay. One, if it is enough, that is only simple. Okay. Now, in sometimes 7.4.3, 7.4.4 is also 7.4.2, 7.4.4. These two theorems are also given in the long answer question. Yeah, that is A and B in the examination paper. 7.4.4. Now, this theorem is a 1-to-1 continuous linear transformation of one Banach space B onto another Banach space. 1-to-1 means given the transformation is 1-1 and onto is there. Now 1-1 onto means that is the homeomorphic mapping. Okay. Any linear transformation which is 1-to-1, then it is through in between the Banach B to B and B dash, then it is a homeomorphism. That is the simple statement. In sometimes that statement is also stated as another second one. In the same manner, that statement is also represented as if a 1-to-1 linear transformation T of a Banach space onto itself of the transformation is also a continuous. At the same time, inverse of that transformation is also continuous. Already, this proof is also we have discussed in the above lemma. Now that is f is continuous and f inverse is continuous. Okay, and just you have to see and refer the above lemma is there. That is 7.4.1. Now 7.4.2, that is state and prove open mapping theorem, and 7.4.4 is inverse of that transformation onto through the homeomorphism. That is also inverse of the part is also continuous. So there are two type of statements. This is one way, and another way is that this is also second same statement is also referred as in this same manner. Okay, that is simple. T is given the part is T be a 1-to-1 continuous linear transformation of a B onto B dash by the open mapping theorem, means just have to reproduce the statement. Okay, but number of students copied papers, please try to understand. Of course, if it is copied, don't produce the theorem 7.4.2. That is very silly thing. You must replacing of this one, just you have to submit the given the statement. Okay, what is the statement of open mapping theorem? What is that statement? T from B onto B dash,
Beyond B dash up to
continuous linear transformation is a open mapping. That continuous linear transformation is a open mapping. Simple statement. Okay. Now, in the proper way, let B and B dash are two Banach spaces. T is a continuous linear transformation, capital B onto B dash. Then capital T is a open mapping.
open mapping.
Okay. That is the simple statement of open mapping. In the replacing of that statement is here. So that a transformation capital T of G is open in B dash whenever capital G is open in capital B and T of G is open in B dash. So capital T is 1-to-1. We have inverse of the inverse is also, we are getting the capital T is there. So capital T means that is the simply cap T of G is there. T or T means that is also stated as T of G. So in the above inequality, T inverse is also continuous because inverse transformation is also a continuous in the above lemma. Okay. So this is end of this unit. Students, listen carefully. How to prove the S of X and R equal to X plus SR? Already, very simple proof, very silly thing. This is open sphere. Okay, S of X and R means X plus SR. Maximum, so many exams are completed here from the beginning of post-graduation in this university. Now, this question is not given, but in my sense, how to caliber the student of caliber. Now, what is the meaning of this one? This is the open sphere. That open sphere, according to the open mapping theorem, now that represented as X plus SR. Here, X be its center and R be its radius. So that value is X plus SR. Now, before the write as the open sphere part, S of X and R equal to set of Y be any one of the element in between the X and Y of the distance is less than R. This is the simple distance, simple metric part is there. Now, for the open sphere part, here Y belongs to S of X and R. This is the meaning of Y belongs to S of X and R. So, this is the meaning of distance from X and Y less than small r. That is the meaning of this one. So, in between the norm Y minus X. So, this is the meaning of distance when the distance is less than radius. So, norm Y minus X is less than R. Y minus X represented as, that is Z is there. So, norm Z is less than R. So, Y equal to, according to this one, Y equal to X plus Z. So, if and only where norm Z less than R means Z is the consisting of R be its radius of the open sphere of the part. Z be any one of the element of given the open radius. So, Y is consisting, SR means X plus SR. Simply, SR means X plus SR. Okay. Now, that is the meaning of Y belongs to, Y is also consisting of X plus replacing Z by SR. So, X plus SR. That is the simple proof. Students, just you have to practice 7.6.1, 7.6.2, some maximum. That is the variety of the paper. Means that is also short answer questions is also given in this manner. Okay. Show that SR equal to R of S1. Now the entire all the representatives in the above lemma is there. Okay. SR means set of X be any one of the element norm X less than R because center at origin dividing throughout by R. Already we have discussed here. So enter the value is Rx means R set of X from norm X less than 1. So this already this representation is also proved in the lemma is there. So that is simply R of this value is S1. So suppose this is less than 2 is there. So that is S2, RS2. Okay. So S2 can SR equal to RS1. SR plus 1 equal to R plus 1 of S1. Okay. So that is the simple proof. Okay, students, 7.6.3. So in sometimes that is also given here. There is no problem. That is the simplest part. Now 7.6.5. Now maximum number of times this question is given in the short answer question. The set of rational numbers Q is the first category in script R. Already this problem is we have discussed in the first year real analysis. Okay, students, once again I am telling this one. According to the functional analysis, we simply understood the operator theory. That is the 11th paper. If you have to choose the one of the optional 11th paper, that is also simple, very simplest. If it has understood the functional analysis, then automatically easily achieved the operator theory paper. Okay. The set of rational numbers, that is the first category in the script of real numbers. Okay. That is also one of the important or not open mapping example is also discussed here. So that's the end of this unit. Students, please stay on the line. Please stay on the line. Please just you have to see the closed graph theorem. That is the 8th unit. This is the 8th unit, closed graph theorem. Okay. What is the meaning of closed? Very time is very too less. Just to try to understand here. First of all, before the closed graph theorem, we have to discuss what is the graph of transformation. Graph of the Banach transformation, continuous linear transformation. What is the graph? First of all, you have to take a graph of real valued function is already just what is the meaning of the function? How to construct the graph? We are taking the horizontal and vertical axis. Function means vertical axis. That is denoted by y or f. Function of x. Y equals to f of x. That is the graph of the representation in between the x and f of x. F of x means y is there. So x and y means x comma f of x is there. So the pictorial tabulation of the set of x, set of all. So that's why just you have to introduce here. Okay. According to this one, x and y means we're replacing of y by f of x. This is the vertical of the part. So x means that is the horizontal line. Y means that is the vertical line. So x takes according to the x of the values, that is the domain of the function. So according to the domain of the values, completely depends upon the function. So that is denoted by f of x. So that is the graph representation in between x and f of x. So how to define the graph of the function? B and B dash are the two NLS, means normal linear space, and capital D be a subspace of the Banach space. Capital T is any linear transformation in between the subspace and subspace approaches to B dash. So from capital D to B dash. So replacing B by, we are taking the subspace of the part. What is the meaning of the subspace? That is the linear condition. Okay. Subspace means alpha x plus beta y. That is the subspace condition. According to that condition, we are represented that function varies to B dash. That is the image of the normal linear space. So that's why that graph of the transformation of the set ordered pairs means we are taking the one of the element is x belongs to capital D and x comma, and B dash of the element is through the transformation, that is Tx. Here the replacing f by t. So that is the linear transformation, and through the domain of the element, subspace of the element is capital D. So that is small x belongs to capital D is there, and through that subspace element and the transformation element is Tx in B dash. So Tx in B dash is there. So this ordered pair is called graph of T. So graph of T simply, that is the roster form is set of x, that ordered pair is x comma Tx. Here x belongs to capital D. So that graph G of T is a subspace of what is the Cartesian product? Subspace of G of T means that is the graph of T. So that subspace of B cross B dash. What is the addition and scalar multiplication of elements of G dash? That is also very simple. That is the simple representation. There are two. We are taking the simple g of t elements x1 and y1. That is x1 and tx1. This is x2 and tx2. What is the addition? x1 plus x2, y1 plus y2 means tx1 plus tx2. Scalar multiplication is we are taking the alpha be any one of the element with respect to the ordered pair x and y. That is alpha x and alpha y. Here x and y that is also represented in b cross b dash. Here alpha be the field element. That is the simple notion. What is the closed linear transformation? Student, listen carefully. Here that these are all domain elements. Here x1, x2 belongs to capital B, and y1, y2 is also belongs to image of the part. That is tx1 and tx2. In the same manner represented as y1 and y2, that is the horizontal of this part. Okay. So small d is a metric on b cross b dash. Very simple. That is the through the graphical representation. Closed linear transformation. What is the closed linear transformation? There are two non-linear space. You have to discuss the 8.3.1, 8.3.2, and we must discuss the closed linear transformation. There are two normal linear space and dB a subspace of D, and that transformation means T maps D to B dash be linear. That transformation must be a linear. That linear transformation is called a closed graph of G of T. T is closed means what is the meaning of closed transformation? When the graph is closed in B cross B dash, that transformation varies from D cross D to B dash, that is called closed. When the graph G of T is closed in B cross B dash, that is simply represented as the transformation is linear. Okay. When it is the linear, that transformation of the linear is called closed means when that graph is closed. Okay. Now, every convergent sequence, here sequence is xn of points of capital D. Here xn converges to x. So that x is always belongs to horizontal point. Horizontal point is also belongs to domain of the Banach space. So that is that transformation of the sequence means txn of the sequence is also a b dash. That is the convergent sequence of point of b dash. So txn means that is simply represented as the convergence point is y. So this value is an equivalent to that is also convergence point is y belongs to b dash. When these two conditions are holds good, one is the xb is the subspace of capital B, that is capital D. D means subspace of capital B. And second one y equal to tx. When these two conditions are satisfied, that is simply that transformation is called closed. So in the same manner, that graph is closed in B cross B dash. Either this one, student, either simply stated as the closed, and or when we are taking the any one of the sequence of the convergence point is in capital B, so that transformation of the sequence is also a convergent sequence of the point of B dash. Txn converges to y. This is the second way of the closed part. Second way of the definition of closed. There are two conditions here, x belongs to D and y equal to tx. Okay, this is the closed graph theorem. Listen carefully. Now last 15 minutes more. If it is possible, and then after this theorem, we will discuss the, we will just have, I am telling some more important questions in this unit after we will discuss the proof of this theorem. Okay. Let B and B dash there are two Banach spaces. The connected that linear transformation is T. So T from B to B dash be linear, and D be any one of the subspace of B. So according to the definition, we must discuss the statement of closed graph theorem. This is the closed graph theorem, students. 8.4.1, very important. If it is possible, if you have to gain the some previous papers, just you have to see and refer. Number of each and every paper is given, state, open mapping theorem and closed graph theorem. In sometimes that is the short answer question, only statements that is the produced there. If it is not, state and prove open mapping theorem, and according to the closed graph definition, and deduce that the closed graph theorem. That is the long answer question. That is the 10 marks. Okay, there are combining these two theorems, open and closed graph theorem, now that is the given in 10 marks question. That is the long answer question. Okay. Now here B and B dash, there are two Banach spaces. Then the connected map is linear. Now here capital D be a subspace of capital B, and that the transformation is represented as T from D to B dash. That linear transformation is, when it is closed, linear transformation from capital B into B dash. This is the into map. And open mapping is onto part. Okay. B into B dash, the continuous linear, closed linear transformation, when it is, now when it is that transformation B into B dash, when it is closed, and sufficient part is, graph is also closed subspace of B cross B dash. And the sufficient part is, when the graph is closed subspace, then automatically, then the transformation is also closed is there. There are two parts. Given the transformation is closed, if and only if graph is also closed, subspace of B cross B dash. When the graph is closed subspace of this part, given the transformation is, then automatically it is closed. Okay. There are two parts of given the theorem. That is the necessary and sufficient part. That is the if and only if. Okay, students, a very simple proof. Suppose connected the given the transformation T from D to B dash, D is the subspace of B, and capital T is the closed linear transformation. We shall show that graph is already, graph definition is there. G of T equal to set of, here graph definition is X be its center, and the image of the element is Tx by the, depends upon the transformation. Here X is also belongs to subspace of the element. That is the closed subspace of the definition. Okay. Now this is the graph representation of the roster form. G of T equal to set of ordered pair X and Tx. Here depends upon the definition. Here X belongs to capital D. So since capital T is linear, then automatically graph is also a subspace. So given the transformation is linear, then automatically graph is also a subspace. So every point, limit point of G of T belongs to G of T. Every limit point of G of T, that limit point is also belongs to G of T. So we are taking the one of the ordered pair is X and Y. So we are up to existence of the sequence up to n terms, xn and yn. Yn can also be written as txn. That is the graph definition. So xn and txn through the definition of G of T, replacing x by xn. So xn and txn means G of T is there. So xn is also belongs to capital D. That is also a subspace element. So this element converges to xn converges to x, txn converges to y is there. So this is the graph. This graph of the G of T sequential ordered pair element converges to x and y, because this is the horizontal of the sequential convergence point. This is the vertical of the sequential of the convergence point. So enter this element is also converting into this side, xn and txn minus ordered pair of x and y converges to 0. So enter this element can also be written as through the linear definition norm, first ordered pair elements xn minus x, second ordered pair elements, second coordinates of the elements are in the ordered pair txn minus y. So this is norm xn minus x converges to 0, and this is also norm txn minus y converges to 0. Okay. Simply, this is xn converges to x, and they occur through this norm txn converges to y. So automatically graph is T is closed. So here x be the x belongs to capital D, and y is also belongs to y equal to tx. So the limit point x and y can also be written as x and replacing y by tx. So this ordered pair is also belongs to G of T. So that is the definition of given the ordered pair. So then automatically G of T is closed. Now conversely, that is the sufficient part. Just you have to see the theorem. First of all, you are taking the G of T is a closed subspace. Now finally that graph is, what is that? We must prove that capital T is closed. Suppose capital T is a linear and xn converges to x, and xn that converges point is also belongs to D, and txn converges to y. We now show that that transformation is closed. Closed means y equal to tx is there. Okay. We have to show that here x be any one of the element, that element is also belongs to the domain of the element. So that is the subspace of capital B. What is the meaning of y? Y equal to transformation of the part y equal to tx. So xn and txn, that is the g of t converges to x and y. So the simply x and y is also belongs to closure of g of t. So that is the interior of this part. So g of t is closed. We have when it is the element is there, ordered pair element is there. So that graph is closed. We have g of t equal to closure of g of t. So x and y is also belongs to closure of g of t, and same that order pair is also belongs to g of t is there. So definition of g of t, same element is also belongs to capital D, y equal to tx. That is the meaning of t is closed. So by the above theorem is, according to this theorem, we will discuss the direct theorem, closed graph theorem. In the statement, in the examination 8.4.2, so this theorem is also produced direct theorem. State and prove closed graph theorem means this proof is compulsory. You must submit it there. Okay. Now, by the above theorem, according to that theorem, we will discuss the closed graph theorem. So that is B and B dash are Banach spaces. T is a linear transformation of B into B dash. T is continuous means when it is the closed linear, that is the Banach spaces means that a transformation is the linear transformation B into B dash. Though so into map is also continuous, then the graph is closed. And another second way, when the graph is closed, then the into transformation is continuous. So there are two parts in the above theorem is also same proof is also produced here. Okay, just you have to see and refer. This is the closed graph theorem proof. Don't mislead here. Okay, this is the closed graph theorem 8.4.2. By the above proof is also in the same manner we will discuss in the first part of. Now, this theorem is also, this proof is also very simple. Okay. Okay, that's enough. Students, now this in this session, especially closed graph theorem is also very simple. Okay, now if you have to understand understood the closed graph theorem, and according to the first 8.4.1 is also just you have to see in this one 8.4.1 according to this one, just you have to we must derive the 8.5.2 directly. This is the closed graph theorem. Okay, so that is very simple. Okay, students, now this theorem is also where only identification purpose, this is not necessary here. Okay, 8.4.3, if in sometimes that is also given. Okay, sometimes this is also given direct theorem in the 8.4.3 for 10 marks. Okay, that is the unique representation. So unique representation means the sum of any two variables in the unique expression is say z, here z be any one of the vector in capital B, and in the direct product, this is the direct sum of the in between the two linear subspaces, say that is capital B. Okay. Now here M and N are both are closed in capital B, and B dash is also a Banach space. So this is the representation, very simple theorem. So just if you have any another chance, just you have to see and refer and practice. This theorem is also there. In sometimes, if it is functional analysis paper, if it is of paper, if it is hard, so in sometimes that this theorem is given in the final examination. Okay, but especially these are all linear subspaces representation. That is the unique representation in this theorem. Okay. Okay. Once again, just you have to see and refer this one. Almost all 8 units are completed successfully. Now, that is one of the important theorem, unit 9. That is the principle of uniform boundedness theorem. Students, please note down. State and prove uniform boundedness theorem. State and prove uniform boundedness theorem. ORR, state and prove the principle of uniform boundedness. ORR, in sometimes this theorem is also called Banach-Steinhaus theorem. Banach-Steinhaus theorem. This is the statement of uniform boundedness theorem. Please note down, this is also one of the important theorem. tomorrow we will discuss the only operators part, because tomorrow is the last session. Try to understand maximum. If it is the if you have any chance, please contact us and personally, because this theorem is also very important theorem in the final examination 9.3.1. Without this one, that is not expect the final examination, the functional analysis paper. So that is also simple through the open and closed mapping theorem. And according to those theorem, there are number of bounded linear transformation. That is one of the subset is script B of B and N. That transformation is bounded subset. So automatically capital A is also a bounded subset of script B. P of B and N. Here, what is the capital B? Capital B is a Banach space and NB a normal linear space. And connected the map is script B is there. So script B be any one of the linear transformation in between Banach space and normal linear space. So the set of all bounded linear transformation from capital B to N. So that is the simple subset is capital A. That is represented as TX. One of the subset is transformation is here. Any one of the subset is capital T belongs to A. And so that image of the element is Tx from T belongs to A. This is also a bounded subset of capital N. For small x is also belongs to capital B. Okay, that is the simple statement of principle of uniform boundedness theorem. Now this theorem is very important. Please note down. Don't mislead here. Without this one, you can't expect the final examination. Now, direct theorems. These are all direct theorems in the functional analysis paper. Okay, 9.3.1, 9.3.2. These two theorems are given direct. Now, one theorem is given in the for 10 marks, and another one is also given in the short answer question. In sometimes that is also given in this part. Okay, this application is not necessary here. 9.4.2. This is also given in the short answer question. Okay, please see and hear. Okay, but due to time lag, due to time, because this is only 1 minute more. Already time is over. Don't be misunderstand here. Okay. Okay, this problem is also given in the for 10 marks or short answer. In sometimes that is also given through the Fourier series 9.4.2. Now this theorem, this is the uniform boundedness theorem. Okay, please see and refer here. Tomorrow, very most important class, that is the final class is there. Okay, that final session we will discuss the only operators and inequalities. Okay. Now, once again, don't deviate this unit. This is the unit 9, principle of uniform boundedness theorem. Students, these 9 units are very sufficient in the final examination, and in additional part of and Cauchy-Squarge inequality, Gram-Smith orthogonalization process, and Hilbert space operators. Okay, students, tomorrow we will meet again, say as usual timings. Okay, tomorrow is the last class. And if you have any doubt, please contact us and personally through WhatsApp. Thank you, one and all.
Thank you, sir.
Okay, once
Sir, your
again.
number giving, sir.
Tell me, man. Hello?
Cheppandi, sir.
If you have any doubt.
Number, sir, your number.
9989.
Okay, sir.
4768.
Okay, sir.
33.
Okay, sir. Thank you.
Okay, Nama? Okay, once again, wish you all the best and wish you good luck.
Thank you, sir. What?